is the first time to do it, and it's not very related, or at least it's not directly related to the course content. Okay. So the disclaimer here, first disclaimer, is that it's actually far from being perfect. In the following sense, like I said, I gave this course twice before, and it's not perfect either, but I don't expect that the content will change much in the next few years. It will change here and there, but not very much. But I'm sure that this particular lecture will significantly change 5 years from now or 10 years from now. It will significantly change. Like I said, it's not very related to the course topics, but we'll give you an idea about what do we mean by abstract math. In this course, we will not prove theorems, we will not do pure math, but this is the language that we will speak. So it will give you an idea about what is the language that we will keep speaking during the course, so that if you feel like you're less comfortable with this language, you can drop, or you decide what you're going to do, maybe even stay and not register for a grade or whatever. So what do you want to do? This lecture is like an anticipatory lecture for for too many why questions expected from you guys during the course, because we engineers will always ask why mathematicians do this, why they do that. So it's like expecting these kind of questions and giving answer to some of them at least. The rest you can figure out on your own, or you're always welcome to come up with questions. What we're trying to do here is a glimpse on how mathematicians think. A glimpse on what math is about. A glimpse on why, or actually how math abstraction is useful. So, and the crazy thing is that we're trying to do all of that in a single lecture. So math is actually about numbers, nothing more. Math is about you observe a pattern. You see something that is repeating, you form a conjecture out of this pattern, and you go and try to prove it. So let's give an example. When you see 2 to the 5 minus 2, this is, and feel free to ask questions, okay? And like I said, this is an informal thing. It's not related to the content of the course. So next time will be the very first formal lecture. So 2 to the 5 minus 2 is like 30, right? And if we do it with 3, this is 240. If we do it with 4, this is 1020. And they are all divisible by 5. Right? So from here you form a conjecture. What's the conjecture? Anybody can say something? What's the conjecture that you form from here? What's the conjecture? This is your intuition says. When you see this pattern, what do you form as a conjecture? As a suggestion? What do you see? N to the 5 minus n is divisible by 5 for all natural numbers, right? And you ask yourself, is this true? Is this conjecture true or not? And go and try to prove it. And it's very easy to prove. I will not waste the time of the lecture. We can talk about it after the lecture. It's very easy to prove. And yes, it's correct. Okay, so the thing here, if you want to give a glimpse of how mathematicians think, don't go home. When you prove this thing, don't go home. So mathematicians, when they prove this conjecture, they don't go home. If you're asked in a math problem, prove that n to the 5 minus n is divisible by 5, and you do it, and you cheer about your proof, okay, that's good, but don't go home. Think of generalizations. So, what is special or unique about the number 5? So, why it's not valid for n squared minus n divisible by 2, or n cubed minus n divisible by 3, and so and so? What's special about the number 5? So you think yourself, you think that, well, what about n to the k minus n divisible by k, right? For all k and n natural numbers. And before go and just boldly prove it, just try to play with numbers and examples. So k equal 2, try n squared minus n, and it works. And it's very easy to prove. This is the easiest. K equal 3, k equal 4, k equal 5, you already did it. K equal 6, k equal 7, some few numbers, and if you find the pattern persists, then it's a conjecture, and again go and prove it. And yes, it works for 3. Unfortunately, it's not working for 4, because here it is, here is a counterexample. 2 to the 4 is 16, minus 2 is 14. 14 is not divisible by 4. And also for 6, 2 to the 6 minus 2, this is 62, is again not divisible by 6. And I'm writing this, I'll convert it in a PDF and send it to you. You didn't need to write after me. Or at least you don't need to write what I write. You may write other things. So this conjecture is not true. And it's working for some numbers, but not others. It's working for 2, 3, 5, and 7. So what do you suggest for a modification of this conjecture?
Prime numbers.
Very good. So we're going to do now the following. We're going to say, well, it's not every k, it's every n but k prime, right? And for this conjecture, it's indeed true, and it's Fermat's little theorem. (1640). Okay. So this is how we should think about math. When you prove something, you observe a pattern. You form a conjecture, go and prove it, but don't go home. Think of generalizations, okay? And I will repeat it. So math is about numbers. So let's start with, we should start somewhere. Let's start with the integers. 0, plus or minus 1, plus or minus 2, and so on. What is the intrinsic characteristics about integers? Let me here write. Math is about numbers, yes. Math is about the formula. is about extracting the essential features of the objects. We don't think of applications, we think of what is the essential features. So if we start with the integers, what are the essential features, the intrinsic features? Why numbers are special? What is special about them? So what's special about the integers? Let's see. What can we do with the integers? Well, we can add two integer numbers to get an integer number. So if I have x and y are in the integers, the addition of them is in the integers, right? What else? There is the associativity property, which is, the order doesn't matter much. So x, y plus z, it doesn't matter which order you do first, right? Okay. There is the zero number, special element in this collection of objects, collection of elements, integers. There is a special element such that when you add to any other element, you get the same element. So x plus 0 is x for all 0, for all x, right? And there is the inverse. What do you mean by the inverse? So if you give me any x, I find you an element in that collection, so that when you add it, you get a 0 back. This here is just the negative of x, right? So, okay, if these are really the intrinsic properties of the integers, let's just make them in a very formal definition. So, this definition will be the definition of an object we're going to call a group in math. So, this 4 axioms is for a group G. It's a collection of elements, numbers, for example, and it has an operation like the addition here. If you add any two elements in the group, you get an element in the group. You have the associativity property, you have an identity element in the group, a very special element in the group E, such that if you add E to any x, you get x back for all x in the group, right? You have the inverse element. So for any x in the group, there exists, this weird symbol is there exists, okay? There exists some other elements in the group, some other elements, such that when you add x to this y, you get the identity element back again, right? If you have a question, stop me. So obviously, sometimes we call it, this is the inverse element, x inverse, which here is just negative x. It's inverse with respect to this operation, plus. So now, if this is the intrinsic properties of integers, if we have any other object that possesses the same properties, then we should treat it as if we treat integers. It's exactly, it doesn't have anything unique beyond integers, right? It has the exact same properties as integers. So, like what? Well, examples, we can have like continuous functions, for example. We can add two continuous functions to get a continuous function. We have the zero element. When we add it to any continuous function, we get the same function again. We have the inverse, so it's again the negative, just the negative of the function. The property doesn't have to be addition. So, for example, the rotation matrices. The rotation matrices. If you remember, guys, we should give the symbol, right? Like anything in math. So, rotation matrices, we give it the symbol SO3, right? So, for any rotation matrix in SO3, and I have R1 and R2, two rotation matrices, actually R1 plus R2 is not a rotation matrix, right? So when you add two rotation matrices, you don't necessarily get a rotation matrix. So rotation matrices with the addition is not a group, but rotation matrices under multiplication is a group. Why? Because if I multiply any two rotation matrices, R1 and R2, the multiplication is a rotation matrix, right? Okay, so we can multiply. Do we have an identity element? Yes, indeed, we have identity element, and it's called the identity matrix, and it is in the group. It's one of the rotation matrices with an angle 0, and if you multiply by any rotation matrix, you get the same matrix again. Do you have an inverse with respect to this operation, which is multiplication? Yes, we have an inverse. We have, for any R in the SO3, I can give you its inverse. Actually, its inverse is the transpose. So the transpose is in SO3, and if you multiply it together, you get back the identity element. So it satisfies all the axioms of a group. It's a group. So it behaves like integers. So you should view rotation matrices as integers, just bunch of numbers, right? The same, or another example. I don't think I will have much time, so I'll skip other examples. So this is a group, but actually integers have more. So Z has more properties. What? Yes, it's a group, so we can add inverse with respect to addition, and it has the 0 element and all of that, but we can multiply, right? It's not only addition. We can multiply any x and y in Z, and the result will be in Z, right? You multiply two integers, you get an integer. And we have a unity, an identity element with respect to multiplication. We have 1. If you multiply this guy with any x, you get back x. So this suggests, are you saying that Z is a group under multiplication?
We don't have an inverse.
Exactly, we don't have an inverse. So, but no inverse. So it's not a group, because when you give me any x, I cannot invert it. Actually, it will be a rational, and a rational number is not integer. So no inverse. So this suggests a definition, right? So this is how mathematicians think. You extract the essential features. Well, it's already a group under addition. Okay, and in addition, you have, or moreover, you have, well, we have a multiplication. It's almost a group, but without an inverse, and it has a name in math, like everything. It's actually, the name is monoid, but I will not bombard you with the name. So it's a group under addition, and it's almost like a group with no inverse under multiplication. And we have, so this is group under addition, almost a group under multiplication, but no inverse. And we have the addition.